Okay, this lesson is going to be about acids and bases. We're going to be looking at the properties of acids first, and then we'll look at the properties of bases. So, number one says that acids have a sour taste. So you can think of like a lemon, you can think of a lime, you can think of apple cider vinegar. All of those have very sour taste whenever you drink them or you try them. So acids have a sour taste. Number two, acids change the color of an acid-base indicator. Specifically, acids will change the indicator into a red color. So like for example, litmus paper will change red if you dip it into an acid. Number three, acids react with metals to produce hydrogen gas. And this goes back to one of the lessons where I talked to you about the activity series. So if the metal is more reactive than the hydrogen that's bonded to the chlorine, as in this example, and we did this one in class, it will replace it. So the zinc is more reactive, replaces the hydrogen. The hydrogen atoms have been pushed out and they're looking for something to bond with. So they bond with themselves and they produce the hydrogen gas. And the zinc and the chlorine produce that aqueous salt. So this is where you see the bubbling that was coming out of the liquid in class. I did a demo and we collected that gas into a balloon and then we exploded it. The next slide here, two more properties, talks about acids. When they react with a base, they will produce a salt in water. And in this, I always talk about antacids like Tums or Rolaids or milk of magnesia, anything like that that you take to prevent the acids in your stomach from building up or moving up through the esophagus. They will react with the acid. The hydrochloric acid reacts with the base. Basically, those Tums, Rolaids, they're either aluminum hydroxide or magnesium hydroxide, and they react with the acid to neutralize it. And when they neutralize it, they produce a salt and water. The salt is dissolvable, so you push it out, and the water as well gets just pushed out, right? Number five, some acids conduct electrical current. So here I have a reaction here of hydroiodic acid. It's going to react with water. When it does that, the hydrogen comes off of that acid and bonds with the oxygen in the water and produces this hydronium ion, which is a positive ion. And then the iodide is left by itself, and they're floating around in the solution as positive and negative ions. And because they're positive and negative ions, when you run a current through there, we put some kind of a sensor, right? The light sensor that we used in class, you dump it in there, and you're going to see that the light turns on. So they conduct electricity. The next slide talks a little bit about binary acids. And a binary acid is a acid that only has two elements in it, hydrogen and some kind of an anion, as you see over here at the top. And that binary means two, like a bicycle. So it only contains two elements, and that's going to be hydrogen and, again, that anion. Usually it's something in group 17 or 16. So HF, HCl, HBr, and I showed you how hydrogen bonds with that fluoride ion to produce that hydrofluoric acid, and that hydrogen bonds with that bromide ion to produce hydrobromic acid. So those are binary acids, only have two elements in there. Versus oxyacids. Oxyacids sometimes are known as ternary acids. They have three elements in them, usually hydrogen, oxygen, and some other kind of element, some other kind of anion. And usually that element combines with oxygen to produce some kind of a polyatomic ion. And the example that they have here is HNO3, which is nitric acid, that's the name. But if you look, I circled the NO3, and that's the nitrate ion. So it changes in its name a little bit, and we'll talk about that a little bit later on. But these are trinary acids when they have hydrogen, oxygen, and some other element in there, some other anion. Here I'm just going to just briefly talk to you about how to tell the difference between a binary acid and an oxyacid, and I'll do another little lesson on naming outside of this. So for me to determine a binary acid, number one, I'm going to look for the formula only having two elements. So the only one out of these first four that only have two elements is HF. So that's a binary acid. The other ones have hydrogen, oxygen, and some other element in there, so that's going to be an oxyacid. Well, what if I'm looking at the name? If I'm looking at the name, I highlighted here hydro in the hydrochloric formula name. Whenever I see hydro right here, just like that, that tells me that that's going to be a binary acid. If I don't see hydro in there, then it's most likely going to be an oxyacid. So you see the other three examples in there are all oxyacids. This slide just talks to you about some common uses for some acids. I'm not going to go into detail with this. I'm just going to, have you go through and just read that and look at that. Now we're moving into properties of bases. Bases have a bitter taste. So you see up here sodium hydroxide, uh, ammonium, baking soda. You have some bases like aluminum hydroxide, like those antacids. Those have all of them have a bitter taste to them. Okay. Bases will change the base color indicators to blue. And then three, dilute aqueous solutions of bases feel slippery. So here I always talk about soaps. If you feel like detergent soaps or shampoo or soaps that you rinse your body with or that you wash your hands with, all of them feel slippery whenever you're using them. Two more properties of bases are that they react with acids to produce salt and water. Again, just like acids, combine the two, you're going to get a dissolvable salt and water out of the reaction. And then bases also conduct electricity for the same reason. Whenever I put a base like sodium hydroxide into water and it dissolves or dissociates, I get sodium ions and hydroxide ions. They're positive and negative ions that are floating around in solution. And again, if I put some kind of a sensor in there, like a light sensor, it's going to turn that sensor on, right? That light, it'll turn that light on. The next part is going to talk about classification of acids. So there's three classifications of acids that we're going to look at. The first of which is the Arrhenius acid. And Arrhenius talked about acids whenever they were dissolved into water. So here, whenever it says solution, and if you see aqueous, that means that this acid was dissolved specifically into water, right? H2O. So what is a acid according to Arrhenius? Well, Arrhenius said that whenever I put an acid into water, that hydrogen that's a part of the acid is going to break off of the acid and it's going to bond with the water. It wants to bond with that oxygen atom, right? So any acid that is going to give away a lot of these hydrogen ions, these hydrogen positive ions, sometimes called a proton, is going to be considered an acid by Arrhenius standards. So here in the next slide, it talks specifically about the hydronium ion. And here I wrote an example of hydrochloric acid up at the top. So when it dissociates, you're going to have a hydrogen ion that's produced and a chloride ion that's produced. And that hydrogen ion is extremely unstable. So it wants to bond with something so that it can become more stable. And if you notice down here at the bottom in the reaction, this hydrochloric out of that hydrochloric acid, excuse me, that hydrogen is going to bond with the oxygen that's in the water. And when they bond together, they're going to produce this hydronium ion right here, this H3O plus. And then that chloride ion will be left float around by itself. So that hydronium ion comes from the dissociation of that acid, that hydrogen and that chlorine breaking apart, and now you have these two that are floating around, which that hydrogen ion again is very unstable, wants to bond with something, so it bonds with the water. The base, an Arrhenius base is a substance that's going to increase the hydroxide ion concentration, right? In an aqueous solution, again, in water. So if I take sodium hydroxide and I place it into water, it's going to dissociate into these positive and negative ions, that sodium ion and that hydroxide ion, right? So if I increase this concentration, or if the substance that is dissociated increases this concentration of this ion, then that's going to be considered an Arrhenius base. So let's look at a a couple of examples here. So I've already given you the hydrochloric acid. And again, just in discussion, these two are going to break apart and you're going to get that hydrogen plus ion, that proton. And since it's increasing that concentration, that's considered an Arrhenius acid. And I gave you this example just in the previous slide here. So when these two dissociate, you get an increase in that hydroxide concentration. So that's an Arrhenius base. Down here on the bottom, I'm going to go ahead and skip this. I'll come back to this a little bit later, but it doesn't really have an impact on what we're doing right now. So on the next one, the next slide here, it talks about the strength of an acid. The strength of an acid depends on how easily that hydrogen ion is released by the acid. The more of those hydrogen ions that are released by the acid, the stronger the acid's going to be. Why is that? Well, each one of those hydrogen ions that are released, they're going to bond with a water and they're going to produce this hydronium ion. And the higher the concentration of the hydronium ion is, the stronger the acid's going to be. Okay, so the strength of the acid again is just based off of how easily this hydrogen ion is released. So these are examples of strong acids, and they are strong acids again because they get rid of these hydrogen ions, what's called a 100% ionization. So they will, if I have a million of these ions that are in there, then all million of those, excuse me, if I have a million of these compounds that are in a solution, then a million of them are all going to release a hydrogen ion, okay? And to bond with that water to produce that hydronium ion. So if it gives away these hydrogen ions very easily, it's a strong acid. A weak acid, as I wrote here up on the top, they don't give out that hydrogen ion very easily. So these are two examples of weak acids here. They mostly stay intact. They will only give up very few of these hydrogen ions to produce the hydronium ion and this negative ion. So very few of these are found in the solution. You're going to find that most of these are going to stay intact. Vinegar is another weak acid. So vinegar stays mostly intact as it's in its acid state, or its acid form, excuse me. So they don't really give away those hydrogen ions to the water very well. Then we look at in the next unit here, or in the next little video, I'm gonna talk about the next two. I'm gonna stop that right here, and we'll pick up on the next video with this.